Okay, let's start to look at the code base for our priority queue lab assignment. You'll notice that there are a couple of packages, heaps.various things. And the first one I want to talk about is going to be the JUnit testing, which you'll find in heaps.test. And there is a JUnit test, test MinHeap. So let me just run it first. And so when your implementation is correct, you should see green bars. And I'll go over each of these tests in a minute. But here are the various tests. And the other thing that the test does is in the end it prints out a correct heap of 50 unique integers. And thanks to Tim Huber, who worked with me a couple summers ago, we developed code to print out these heaps in a way that's much more easily understood by the human eye. So here's the root of the tree, and it's printed just like the tree ought to look. There's zero's left child, there's zero's right child, and near the bottom of the tree here's 22, who has children 47 and 41. And you should be able to see that at every point in the tree, the heap property is respected, that 10 is no greater than 24 or 11, 7's in the correct relationship with 25 and 8, and so on. And that code for printing out the tree I'll get to in a little bit. It's not an easy piece of code, but I think it's worthwhile. Having a good debugging tool makes everybody's life easier, and I'm glad that Tim and I went through that work last summer. Let's take a look at these various tests inside test MinHeap. Okay, so this is a bit of code I actually found on Stack Overflow to allow a JUnit test to do something special when it fails. And the special thing that it will do is it will print out the tree before and after the failure, which I think is very helpful for diagnosing problems. So let's look at these tests one at a time. So test empty heap does what it says. It generates a heap of nothing, and the heap after construction should be empty. We make sure that isEmpty is working correctly and that size returns the right answer of 0. Very simple test. Test insert inserts some number of items into the heap. The number is randomly drawn from a random number generator, something between 0 and 99, which will be something between 1 and 100 after we add 1 to it. And so what's happening, every time we do the insert, we're verifying that the size and capacity are in the right relationship to each other. And then these checks are run that I'll talk about in a second, both before and after. I'll get to that in just a second. Okay, so we can see that test insert is simply checking insertion into the heap. And hopefully this will fail early on a relatively small heap with a small number of insertions so that you can debug your code correctly. More easily, I should say. So this is trying to test the extract min. So we insert a bunch of numbers into the queue and then we extract them. And each time we're just making sure that what we get is what we expect to get with the proper checking and so on. There's a couple of tests that use sorting. So if you insert into a heap, the numbers should come out in sorted order. And this is tested both with unique numbers here. First, with genUniqueInts generates a bunch of unique integers. And this one on purpose generates one with duplicates. Your heap is supposed to handle things with duplicates. To be honest, my heap didn't when I first implemented it. And so this bit of code here was leading to failure. But hopefully, like I say, this should help you debug your code more easily. The sorting test simply inserts things into the queue in the order that they're given, and that's a relatively random order. We then make a copy of the data and sort it, and then we compare what comes out. Okay, I'm back. I apologize for that pause, but what happened is I realized I made a copy of the data here, which is good, and I sorted it using a system sorting method, and I was failing actually to compare the result coming back from your extract min with what was in the copy. So I added that line of code, and if I run the unit test, hopefully it's going to pass, and it does, so we're all good with that. Okay, so that's what we have so far in the unit test. What I want to do next is look at what we do to validate the heap. Validation occurs every time this check method is called. So what we actually do in this constructor-like method up here at the top is we generate a new heap of a certain size, but we're wrapping it with a MinHeap Validator. And the MinHeap Validator is able to make several tests on the heap to make sure that it's correct. And every time we call check on that validator, it's doing the checks. Let's see what those validations consist of. That's in the validate package. So here's the MinHeap Validator. And I put in some comments. There's this before instance variable that's capturing the state of the heap before we do some work. And so when check runs, it's doing two basic checks I'll talk about in a second, and then recapturing before when it's done for the next call to check. And if anything does go wrong, what it does is it prints out the tree before things went wrong. It tells you what went wrong, and then it shows you what the tree looks like now. I found that very helpful in debugging because you can follow what's happening to the tree. So what are these two tests that we're going to do? Let me talk about this one first at the bottom. So remember from lecture that your binary heap is supposed to be nearly complete. And so that means that between the beginning and end of the heap, everything should have some business to do with the heap. There should be some real elements in there. So this check for gaps is simply making sure that there are no null entries, that's this part here, in the current active part of the heap, which goes from 1, remember we're skipping 0, up to pq.size inclusively. Okay, so that part I think is fairly straightforward. But the other check that I do here is not so obvious, though I believe it is necessary, and I explain why in the comments. So past where the size of the heap is over with, but there's more capacity, so after the last valid element in the heap, this code is going to make sure that every entry there is null. And I wrote down here, you might say that your heap would function correctly even if we didn't have nulls there. So what happens is your heap has elements in it that reference storage. And those references contribute to the liveness of each object that they reference. And if we left references in the heap past the live part of the heap itself, and by that I mean up to pq.size inclusively, then our array is referencing objects in an area of the array that really isn't being considered by our program. And that's going to contribute unnecessarily to liveness, and if we're the only reference left to that object, it's going to hang around when it really should die. This is a very important principle when you design software, which is not to artificially extend the lifetime of any object. And so to make that work, and this certainly doesn't violate any asymptotic claims we're going to make, what we want to do is whenever we decrease the size of the heap by 1, we make sure that that element that we just decreased past is null. Okay, so that's what check for gaps does. Check for no nulls in the active part of the heap and make sure everything else is null. And if anything's wrong, it throws an error. Now the other test is probably what you would expect, that the heap property is maintained. Remember, every parent should be no greater than either of its children. And so the converse is true also. Each child should be no smaller than its parent. And so this code just loops through the active part of the heap, making sure that every node that has any children respects the heap property and that the parent is no greater than its child. And we check both left at 2 times I and right at, we check both right at 2 times I plus 1, that's done here. And we check left here at 2 times I. Both of those tests are made, and then if there's anything wrong, we catch both errors at the same time and tell you about it. Okay, so that's the MinHeap Validator. The one last thing I want to talk about in this particular video is the timing code. So inside Heap.Test there's Heap Timer, and this is very much like the list timer that we used in Lab 0. But what we're doing for the body of our work here is inserting random numbers into the heap, some number n, up to some number n. And then we're extracting that as well. And so this should show us the amount of time that we're spending doing n actions into the heap. We expect this is going to take n log n time. So I'm going to run this. I'll start it running, and then I'll pause the video until it's done and come back and show you the results. So here we are running this particular timer, and I'll pause. Okay, I'm back, and about 5 minutes has elapsed in the creation of these timing results. So this is something you probably want to do near the end of your work. It wouldn't hurt to wait until you're got a bit of time to see it happen. In order to see the results, they're in the outputs folder. Remember, we have to refresh that. When we do, we see this prioq.csv has been created. For these various sizes, this shows us the binary heap, and I'm just going to select those. And then with my chart, I'm going to plot them like we did before. And that's actually a pretty good curve. So we expect this to take n log n time. So you can see this has a little bit of a lift to it. It's not exactly a straight line. If you wanted to try to simulate a straight line that might somehow match this curve, you could do it this way. So I could take two values, for example, these two. So here's 230. And to get to 257, I add 27. So I'm going to say that's equal to C8 plus 27. And then what I'm going to do is I'm going to drag this down. And what this should do is give me what would be a straight line next to that other data. And I just started a little bit after the beginning just to give the curve a chance to get settled. If I look at this, well, let's see, that's not what I wanted at all. Why did it do that? Hang on a sec. I'll do it again starting from the beginning. So let's do 91, and that's equal to C2 plus 9 and 5 is 14. Okay, let's drag that, and that should give us something linear to look at here. And if anything, we'll see that the shape of the curve, here I'll just put linear up here, we'll see that the shape of the resulting curve ought to be linear. So let's look at this scatter plot. Yeah, so you can see a straight line, even if this were measured over here, a straight line would continue in a way that's very different from the n log n curve once you see the straight line there. So this little bit of lift is actually the log n multiplier that we expect on the binary heap, and this is a pretty good result timing-wise. These numbers are generated randomly, and for some heaps, depending upon the way the numbers fall, you do more or less work when you heapify. And so it's going to be a little different from run to run. I did modify our timing code in the following way. Let me show you that. So let me quit this. So in the timing package, and this is going to happen in your repositories as well, in this timed runnable, but what we used to do is take the fastest time, and I put in some comments about this. Because these are random results, the fastest time really isn't reflective of a worst case heap. I don't want to take the worst case time either, because the worst case time could be due to interference on my computer. So I think what makes sense is to find the median time. And so what I do is I use the built-in priority queue that Java has, and I just sort of go halfway through it, num times divided by 2, to get the median result and return that. And that seems to be working pretty well. I was trying the fastest result initially, but some of the data just happens to be too quick, really, to exhibit all the behavior we want to see from Heapify. So the median result seems to be a much better thing to do. So let's see, one more thing to show you, and then I'm going to stop this video and start another on the actual assignment, and that is in heaps.util, there is this code that Tim and I wrote that prints out the tree in a nice form. Now there's two main static methods. One is toTree, which takes the heap and makes it look like the trees that I've shown you before. They look quite nice. They're it's easy for a human to see what's going on with a heap like that. And there's a toOutline method which produces kind of a indented structure of the tree. Computer scientists are used to looking at that, but it's not as pretty as the one you get from toTree. So for that reason, the toString inside the heap MinHeap that I'm going to give you is going to call toTree by default. And the code for doing that, that's going to format horizontally, which is down here somewhere. Format is tree, here it is not simple. But like I say, I'm glad we did this, and I think it ends up with a better result. You're welcome to take a look at this code and see how it works. If you have any questions, feel free to ask me, because I think I did actually write this part of the code. Okay, that's the end of this video. The next one we'll talk about the assignment itself.